Green's theorem, Stoke's theorem, Gauss's theorem, that's the divergence theorem, and the fundamental theorem of calculus. Those are all actually the same theorem. What I want to do today is explain how I can unify all those different theorems and view them all as just various instances of a single greater truth. This lesson does require just a little bit of background, so if you're not familiar with Flux and Flow, Stoke's theorem, Green's theorem, or the divergence, I have videos of them on my channel, and I've linked them in the description. Unification is a statement about a relationship between a differential operator. That's a way of measuring how much a vector field is changing, and it's a generalization of the concept of taking the derivative. And a corresponding vector projection on the boundary. So in Calc 3, we have two different kinds of differential operators, the divergence and the curl. And we have two ways of projecting the vector field onto a unit vector on the boundary. You could either project it onto the outward normal here, or you can project it onto the unit tangent there. And I want to explain that the divergence corresponds with a projection onto the unit normal vector, and the curl corresponds to a projection onto the unit tangent vector. And it actually really makes sense. Let's just imagine a region. I have two regions drawn, and in the first scenario here, I want to suppose that at a point there is positive divergence at that point. My drawing isn't perfect here, but whatever. You can actually see I finished drawing the positive divergence at that point. I think you can already see why this corresponds to projecting onto the normal vector. In fact, if I draw a normal vector right there, you can see that the divergence at a point would produce vectors that are actually going in exactly the same direction as a unit normal vector. And likewise, in this picture, suppose that I had positive curl at this point. So I have a whole bunch of vectors curling around here. And then right here at this point, if I drew a unit tangent vector on the boundary, you can see that it would actually be going in the same direction as that positive curl right there. So it really helps me to imagine that divergence is what would cause the vector field to flux across the boundary. And if you had positive curl, that spinning at this point right here, this spinning at that point right there, if you had a particle on the boundary, that spinning would do some work to push the particle around the boundary. Okay, we are actually ready for the statement of unification. This is the statement that unifies all the fundamental theorems. If you have a vector field, and you calculate the sum of the differential operator everywhere on the interior of the region, that will always give you the same answer as if you calculate the sum of the corresponding vector projections on the boundary of the region. So it's a statement about a relationship of adding up a bunch of things on the inside of the region and adding up a bunch of things on the boundary of the region. And it always uses this correspondence. Divergence always corresponds with the vector projections, the projections onto the normal vector, and the curl always corresponds to the projections onto the tangent vector. So this is a lot. That's a very dense statement. So my way of unpacking this is just going to be to take some of our fundamental theorems and use this statement and check and see if they really do generate these fundamental theorems. And I think actually it's kind of awesome. This is my favorite thing about this is when you do this, kind of the coolest one is when you use this unified statement in order to generate the fundamental theorem of calculus, the very first one of these that you learned all the way back in Calc 1. All right, here we go with the divergence theorem. I wrote it down here. Let's check and see. Does this work? Is it consistent with this unified statement? So what the divergence theorem says, if you're calculating the flux through the boundary, that's the sum of all of the projections of the vector field onto the unit normal vector everywhere on the boundary of the solid. Then that's the same thing as if you add up the divergence everywhere inside the solid. So So it absolutely does. Here what we're doing is finding the flux through the boundary. So that's the sum of the vector projections on the boundary of the region. And the other thing that you can do is add up the divergence everywhere on the interior of the region. So the divergence theorem is absolutely the same thing as this unified statement here, and the correspondence works, right? Divergence corresponds with projection onto the normal vectors. Yay, it keeps working. Okay, so here I'm doing Green's theorem and it's still checking, right? Okay, so when you look at Green's theorem is a statement about, here I put down the one for flow. So here I have C is the boundary of a region R. So now we're just in 2 dimensions. And if the statement is, if you want to calculate the work along a boundary, all you need to do is add up the curl everywhere on the interior of the region. So there it is. I am calculating the sum of a bunch of vector projections on the boundary, and that always gives me the same answer as if I calculate a bunch of differential operators on the interior of the region, and the correspondence matches. Curl corresponds to the unit tangent vector. All right. This is my favorite. I'm gonna just say this is my favorite thing about calculus. What I want to do now is try to take this unified statement and see if it actually predicts the fundamental theorem of calculus. So I have the fundamental theorem of calculus written down. And what this statement is telling me to do is to add up the differential operator everywhere on the interior of the region. So just to be clear, in the fundamental theorem of calculus, the regions that you integrate over are just one-dimensional objects. So what I'm going to do is I'm going to choose this, capital F, right here to be a one-dimensional vector, and inside that one-dimensional vector is the function. And then when you calculate the divergence, all you're doing is the one-dimensional gradient dot product with this one-dimensional vector. So it just means take the derivative. So that's what you have there. You have f prime of x. So actually, this left-hand side here does actually follow this, the sum of the differential operator everywhere on the interior of the region. That is what you're doing on the fundamental theorem of calculus. So actually, this f prime of x right there is really a simplified form of the divergence. Now let's check the second half of this statement. So the second half of this statement says you need to calculate the sum of the corresponding vector projections on the boundary of the region. Okay, so since I have the divergence right here on the left-hand side, adding up everything on the inside, what I need to do is find the corresponding vector projections on the boundary. So I need to somehow produce normal vectors to this region. Well, this is a one-dimensional region, so the only way that I can produce a normal vector is by producing an outward vector right there, and it has to be a one-dimensional vector and it has to be a unit vector, so that's just the vector 1. And on the left-hand side, I have to produce an outward normal vector here. So since the left-hand side outward is in the negative direction, that means this outward normal vector is going to be -1. Okay, so what are the values of the function on the boundary? So the value of the function on this boundary is f of b, and the value of the function on this boundary is f of a. So what I need to do is calculate the projection of this value onto that vector. So what I need to do is calculate f of b dot product with 1. Okay, so that's just f of b. And likewise, on the left-hand side here, if I calculate the vector f of a projected onto the outward normal vector on the left-hand side, all I'm going to get is negative f of a. What this thing says is I need to do the sum of all of the corresponding vector projections on the boundary of the region. There's only 2 boundaries. Okay, and I added the, and I have the both of these vector projections right there. So this is the sum of the corresponding vector projections on the boundary. So this is just so beautiful. Okay, let's just take a minute to appreciate how awesome this just puts these 2 beautiful bookends on the theory of calculus. You do all this work in Calc 1 in order to lead up to this thing, the fundamental theorem of calculus. And you go through all this business with Taylor's theorem and then all this vector calculus stuff. And at the end of it, you arrive at this statement right here, which is a very general statement and predicts all of these different versions of the fundamental theorem of calculus. And it does correctly predict that thing you learned all the way back in Calc 1. So the fundamental theorem of calculus really is the one-dimensional version of the divergence theorem.